All right, so we got our displacements for the pink areas, and I had a little bit of a plot mistake here where it should have been at the -5 meters per second. We got it sorted out. Now the next step is to find the total displacement. How could I use this information to figure out the total displacement? Yeah, add them up. We've been here before. We've done this in homework, right? So we say delta D total equals, and we could write it out formally, delta dA plus delta dB plus delta dC, and so on. And I think just for the sake of space, I'm not going to sub in all my values. I'm going to do a bad thing. Can you guys tell me quickly? Can you do this math? What's the total displacement going to be? Yeah. Yeah, it looks like these guys cancel each other out. 50 meters. Sorry, 15 meters. 15, 1-5. Positive 15 meters, or we could say 15 meters to the east. All right, well that's great. That's some things that we were able to do with vectors and position information previously, but now we're doing it with velocity time information. So we're kind of like building up. We're leveling up, increasing what we know. I want to take that graph that we did up above, and what we did before was we translated a position time graph into a velocity time graph. I want to suggest that we could do the opposite. We could, given enough information, translate a velocity time graph into a position time graph. We could go the other way around. So I want to take this information that we've kind of figured out and turn it into a position time graph. I want to go the opposite way, decoding. And so if we're going to do that, we're going to have to give ourselves an axis label, position, meters, going to keep east positive. Now, I've thought through this data already, but I want to map out what my thinking was, okay? Let's think about how we would scale this. What's the furthest that we went? How could we figure out the furthest that we went in order to set our vertical scale? Take a look at this data. 5 meters. When I get to the end of this portion B, have I gone 10 meters or is the displacement cumulative? I'm seeing people mouth it. Somebody say it out loud. What is it? Have I gone 5 meters or 10 meters or 15 meters by the time I get to 4 seconds? Is there anybody who's brave enough to say? Yeah? 15. It's cumulative, right? It adds up. This portion gave me 5. This gave me an additional 10. I've done a total of 15 by the end of 4 seconds. So that means that by the time I get to the end of 5 seconds, how far have I gone? 17.5, right? So you know what? It seems to me that maybe I want to think about how I can fit this on here, like to actually fit my data in place. I think I could probably say like, okay, is it really 15? No, it's 17.5, isn't it? 17.5, yeah. So I think I can fit it on. I can say this is 5 meters, this is 10 meters, this dot here is 15 meters, and oh my gosh, this last little bit, doesn't that just hit 17.5? If each square is 2.5. Just barely scaled this one properly. And we got time in seconds. Now I realize that I go 17.5 meters to the east, but do I ever actually double back fully to the west? So I don't actually think I need the bottom half of that graph. I'm going to leave it empty because rationally I think that it's just maybe not even useful this time. I got to think about my timing. The rule that I said before was that if I've used this graph and I'm translating to this graph, I'd like to preserve a stacked time axis. So I'm going to use the same scaling just so that I can see that conversation play out in a vertically stacked way. So this is still going to be 1, 2, 3, 4, 5, 6, 7 seconds. And I got to figure out, my goodness, where should the points be? Well, it turns out that at the end of 2 seconds, how far have I gone? 5 meters east, right? So that's at the end of 2 seconds. So I got to come down here and say, okay, well, my position at the end of 2 seconds is going to be 5 meters to the east of the origin. But then at the end of 4 seconds, how far have I gone? Remember what we said about cumulative. How far have I gone in total at the end of 4 seconds? 15, right? I mean, I could say it's 5 plus an additional 10, or I could say at the end of 4 seconds, I've gotten to 15. Depends on how you think, I suppose. But either case, my new position should be 15 meters away from the origin at the 4-second mark. And then I say, okay, well then, what is that? Looks like it's at the 5-second mark. At the 5-second mark, which should my position be? 17.5, it's cumulative. And then at the 6-second mark, where should I be? Back to 15 again, right? All right. All right, so actually, you know, I'm tempted to do some sort of a curve of best fit, not a line of best fit, because I feel like this is going to follow sort of a curvy path, right? But I got to think about what's happening. And I think, hey, listen, I got this story that I told once upon a time. It turns out that as I travel those first 2 seconds, I'm going to go faster and faster. Isn't that what the story told us? And fastness on a position time graph is slope. See how this story all ties together? This is a rich tapestry where every thread is interwoven, right? Like I'm all the way back. I'm using everything on this darn page, right? Come back down over here and I say, hey, if I speed up, the slope should get steeper as I approach this position in space. All right, I can plot that. Steeper. It got steeper. It's curved. All right, the next story that I'm going to tell is that it goes east at a constant velocity. Again, I'm thinking to myself, constant velocity, that means constant slope. So I come back over here and I say, okay, well, as I tell this story from 2 to 4 seconds, my story is one of a constant slope. Isn't this nice the way it all ties together? Like it really is a whole story, like looked at from different perspectives. Part C says, okay, well, there was uniform negative acceleration, ultimately coming to an arrest for an instant. Now, if I'm traveling towards the east and I'm experiencing negative acceleration, we discussed this, aren't you slowing down? So, and somebody even wanted to say decelerating. So I'm slowing down for sure. And if I'm slowing down, what should be happening to the slope of this graph? Less and less, right? Slowing down, less and less slope. So I come back to this position time graph. That means, okay, it'll start off kind of slopey, but by the time it gets to the top, if it comes to rest, shouldn't the slope ultimately be 0? Because a slope of 0 means a speed of 0, right? So that means that when I get to the top, it's going to flathead right there. It's going to flatten off. That means that this graph is going to go up and it's going to curve to a 0 slope at the top. And there's a part of me that wishes this graph was bigger, but I couldn't get the whole story onto one page if I made the graph bigger. So make sure that it looks like flat on your graph, okay? Then the part D, it says it travels west with a negative acceleration and speeds up. Okay, so if it's going to go west, that means that it's going to be less east, right? So right now I'm very east, and if I'm going to go west, yeah, I've gone less east, I'm more west. But it also says that it's going to accelerate negatively while it travels negatively. That means speed up. So again, if I start from that instantaneous stop, I'll get slopier and slopier, and it'll curve down. Remember, slope on a position time graph means velocity. So now we've got this negative velocity, which makes sense because I was traveling backwards at that point. All this stuff ties together. And I'm being silly when I say rich tapestry, all the threads woven together, but doesn't it kind of feel like that? Like there were a lot of threads here, and we actually did. We tied them all together in one picture. And it's just a car that's going down the road, going out of cruise control, and then turning around and going in reverse. But boy, physics seems to sometimes make the simple seem complicated. But at the same time, once you understand the language and once you understand what we're doing here, you just be like, oh yeah, that makes total sense. Okay? We want to make sure that we're processing it, we're doing the homework, so that you can just come back to this and say, oh yeah, that makes total sense. That's the goal. Okay? That's all I gotta say about that.